identifying proportional relationships in tables. So up until this point, we've talked a lot about rates and ratios and finding unit rates. All of that is leading us up to working with proportional relationships. So first, we are going to take a look at those proportional relationships and what they would look like in a table. So we know that giant tortoises and turtles in general, we like to say, move at a very slow pace. But we want to know, is that pace slow and steady? Steady meaning constant. Okay, so use the table below to determine if that is a constant rate of speed. So constant meaning that it's the same throughout. So whether I go for 2 seconds or 1 second, is that distance that I'm covering equivalent? All right, so let's take a look at how we're going to do that. So first I have to look at what I know about the rate of speed. I know the rate of speed is always found when I do distance over time. So I can take this first relationship and look and see that this tortoise does go 3.5 inches in 1 second. Now the nice part is this is already my unit rate because I am comparing 3.5 inches to 1 second. So in order for all of this table to have a proportional relationship, each of these different ratios has to be equivalent to 3.5 to 1. So what we're going to do is we're going to set up each of our rates, and then we're going to use those rates to find the unit rate. If they are all equivalent to 3.5 to 1, then it is a constant rate of speed. If it is constant, so if we do have these unit rates and they are all equal to 3.5 to 1, that's what we call the constant of proportionality. Notice that word constant is in there again, meaning that we continue to see it. It's always there. So if we always see a unit rate that's the same, then it can be a constant of proportionality. Let's take a look. So first I have my second set of numbers and my distance, because it has to be set up consistently throughout. So my distance is 7 inches and my time is 2 seconds. So I want to know that what I get when I'm going to a unit rate, and I want to know how far does he go in 1 second. So to determine that, I know that I have to divide 2 by 2 to get to 1. And when I do to the bottom, I have to do to the top. So then what I can do is, if I need to, I can always pull up that trusty calculator and I can check and see. So 7 divided by 2, and it does give me 3.5. So far I do have a constant rate of speed. So for the first 2 seconds, that rate is constant. So these two things, so if I highlight it in yellow, we're going to go ahead and say that they are equivalent. All right. So then my next one would be my 10.5 and 3. So the tortoise traveled 10.5 inches in 3 seconds. Again, I want to know what is that equivalent to if he were only to travel for 1 second, so that unit rate. To do that, I have to divide by 3. Right, and then we can always work this out by hand too. So I have 10.5, and I want to divide it by 3. 3 goes into 10 3 times. Minus 9 is equal to 1. Bring that decimal up. Bring that 5 down. 3 goes into 15 5 times. And I get 3.5. So far after 3 seconds, this tortoise does have a constant rate of speed. But can I just stop there and just assume that this works? Absolutely not. You have to check every rate inside of that table. So here we go to the next one. We have 14 inches in 4 seconds. And again, I want to know what that's equivalent to if he were only to travel for 1. I divide both sides by 4. Right, and when I divide both of those sides by 4, again, I am going to use my calculator just to make this go a little faster. So I have 14, and I'm dividing by 4. And once again, I get 3.5. So far I'm doing really well. Well, the tortoise is doing really well at staying at a constant rate of speed. All right, so I've gotten this one. Now I am moving on to my last one, which is 17.5 to 5. So if I have 17.5 to 5, again, I want to know what is that equivalent to if the tortoise were to travel for 1 second. I know to do that, I have to divide by 5, and I have to do that to both the top and the bottom. Again, we're going to pull up that calculator, so 17.5, and I'm dividing it by 5, and sure enough, I get 3.5. So this tortoise, no matter how long he's walking for, he walks at a rate of speed that is equivalent to 3.5 inches in 1 second. So because of this, I can determine that yes, this is a constant of proportionality. Or I'm sorry, yes, this is a proportional relationship. And the constant of proportionality is there we go, and I have to go back and I have to look at those numbers. 3.5 inches, and I can put my line, I can put 2, I can put per. So the constant of proportionality is 3.5 inches per 1 second. So this does a really good job of describing what the constant of proportionality means. If we just want to know what the constant of proportionality is so that way we can use it in an equation later on down the road, it would just be 3.5 per 1, which we also know is equivalent to just 3.5. All right, so let's take a look at the next page. We are going to take a look at this table that has the distances that Allison drove on one day of her vacation. And we're going to determine if the relationship between the distance and the time is proportional or not. So you can always try this problem on your own and come back and check your work to see how you're doing. Otherwise, you can continue to work with me. The nice thing here is, once again, they have given us our unit rate. Okay, and we know we do distance over time. And in this case, she goes 65 miles in 1 hour. So in order for this table to have a proportional relationship, every single one of these has to be equivalent to 65 miles to 1 hour. So start here. I have my 120 miles. So Allison drove 120 miles, and it took her 2 hours to do so. So what is that equivalent to if she were to have only driven for 1 hour? So now I'm going to take and divide. And I know to go from 2 to 1, I divide by 2. What I do to the top, I do to the bottom, and vice versa. Here I have 120 divided by 2. And I can use my shortcut and say 12 divided by 2 is 6. And then I add that extra 0 here, and I get 60. Well, right off the bat, we're finding that in her second hour, she drove 60 miles per hour. Is that equivalent to 65 miles per 1 hour? The answer is no. So because of the fact that even in the second hour she deviated from that speed just a little bit, we can determine that this is not a proportional relationship. So this is not a proportional relationship because there is not a constant of proportionality. And we know that there isn't a constant of proportionality because the unit rates aren't the same. So I can't stress this enough. For a unit rate to be a constant of proportionality, all the unit rates have to be the same. Right? I would strongly encourage that you write that down somewhere in your notes and like bold, big circles, exclamation points, because that is incredibly important. If you can nail down the fact that a unit rate or any relationship that has unit rates that are all the same, then the unit rate becomes the constant of proportionality. You are good to go.